Friends, we'll proceed for a new concept, new chapter called as error function. Now we are going to take two formulas, or we can say that mathematical definition. One for error function of x, and number two complementary error function of x. Whenever we take error function of x, the formula is 2 upon root pi integration from 0 to x e raised to minus u square du. You can observe that here error function of x we are talking about, and x is reflecting in the upper limit of the integration. For example, if I want to say that error function of a, then limits will be from 0 to a. If I say that error function of y, then limits are 0 to y. In definite integration, variable is never important, and therefore instead of u square you may have any other term also. For example, you may have e raised to minus t square dt, you may have e raised to minus m square dm. Now this is called as complementary error function of x, and now in complementary error function of x reflects as the lower limit of the integration and upper limit is always infinity. Remaining terms, that is 2 upon root pi and e raised to minus u square du as it is. Again same concept, if you want to say that error function of a or other complementary error function of a, so it will be 2 upon root pi integration from a to infinity e raised to minus u square du. Here also variable is not important, you may have variable as y, t or any other variable, whatever you want to take. And now we will take four important properties of error function that we require while solving the example. We have to remember all these properties, and this can be proved very easily using the concept of definite integration or by using properties of definite integration. Number one, error function of infinity is always equal to 1. Number two, error function of 0 is always equal to 0. Number 3, error function of x plus complementary error function of x, that total is always equal to 1. And number 4, error function of minus x is equal to minus error function of x. In other words, we can say that error function is an odd function, because you know that for odd function f of minus x is always equal to minus fx. So this satisfies the condition of odd function, and we have to remember all these four properties. Now after understanding these four properties, let us proceed for the next concept. After properties of error function, let us take new concept, that is derivative of error function. Example is find d by dx of error function of ax. So by definition, first of all, we are going to write down error function of ax is equal to 2 upon root pi integration from 0 to ax e raised to minus u square du. Differentiating variable is x, so d by dx of error function of ax is equal to, now we will apply the concept of our earlier topic, and that is D.U.I.S, differentiation under integral sign, because in RHS we have to differentiate this integration. We can observe that differentiating variable is x and integrating variable is u, and therefore we have to apply the concept of D.U.I.S. Second important concept, our differentiating variable is x and x is present as the upper limit, and therefore we have to apply Leibniz rule of D.U.I.S, and then we will apply Leibniz of rule of D.U.I.S in this manner. 2 upon root pi as it is, integration from 0 to ax dabba by dabba x of e raised to minus u square du. As per the Leibniz rule, we are going to replace integrating variable by its upper limit now. So it is e raised to minus a square x square multiplied by derivative of the upper limit minus replacing u by lower limit, that is 0, multiplied by d by dx of 0. So this is nothing but Leibniz rule of D.U.I.S that we have applied. Simplifying further, so 2 upon root pi in bracket, we can observe that derivative of e raised to minus u square with respect to x is 0 plus e raised to minus a square x square into derivative of x is 1 and therefore a as it is, and minus last term is also 0, and therefore we get the value of derivative of error function of ax as 2a upon root pi e raised to minus a square x square. Next topic is integration of error function. We have to integrate error function of ax within the limits 0 to t. Whenever single term is present inside the integration, we know that we always have to take 1 as a multiplier, and therefore while integrating this error function of ax, we will take 1 as a multiplier, and as per LIAT rule, we have to take error function as u and 1 as v, and applying by parts. So it is error function of ax into integration of 1 dx within the limits 0 to t minus integration 0 to t d by dx of error function of ax multiplied by integration of 1 dx dx. So this is our regular formula of by parts we are applying. Simplifying further, error function of ax into integration of 1 is x, and then within the limits 0 to t minus integration from 0 to t. Error function of ax we have proved just now, formula is 2a upon root pi into e raised to minus a square x square multiplied by integration of 1 dx is x, and then we have to simplify it further. We are going to put upper and lower limits here. So replace x by t multiplied by error function of at, and lower limit is 0 minus a upon root pi integration from 0 to t e raised to minus a square x square multiplied by 2x dx. For sake of convenience, we are making a group of 2x, and this is the integration by substitution. So let us do the substitution. A square x square is equal to u. A square as it is, differential of x square is 2x dx is equal to du, or we can write down 2x dx is equal to du upon a square. And also we can observe limits are going to change as far as upper limit is concerned. So t into error function of at as it is minus a upon root pi into integration. When x is 0, u is 0, but when x is equal to t, we get u is equal to a square t square e raised to minus u, and 2x dx is nothing but du upon a square. Then next step is t into error function of at as it is minus 1 upon a root pi. We can observe 1a gets cancelled into integration of e raised to minus u is e raised to minus u upon minus 1, and therefore we can write down limits as it is 0 to a square t square. Then let us proceed for next step, t into error function of at plus 1 upon a root pi as it is, and now we have to put upper and lower limits as e raised to minus a square t square minus e raised to 0, and that is equal to 1. So this is called as answer for integration of error function of ax dx within the limits 0 to t. Let us solve certain examples to understand the concept of error function in detail. First example is integration e raised to minus x square dx within the limits a to b is equal to root pi upon 2 error function of b minus error function of a. Better to start from RHS. So let us start with RHS, which is easy to solve. So RHS root pi upon 2 into bracket. Now we are going to write down the definition of error function of B. You know the definition, 2 upon root pi integration 0 to B. We know that when you talk about error function of B, upper limit is B. When you talk about error function of A, upper limit is A. Here e raised to minus x square dx, as we discussed earlier, variable in definite integration is not important. Here we have to give the answer in terms of x, so better to take integrating variable as x, minus 2 upon root pi integration from 0 to a e raised to minus x square dx, that is equal to root pi upon 2. It is better to take 2 upon root pi common, and then we are going to write down, I am going to write down second term first, minus 0 to a e raised to minus x square dx plus integration 0 to b e raised to minus x square dx, that is equal to, now this root pi and 2 cancel. We are going to use the property of definite integration. We know that whenever we change the sign, limits are interchanged. So I am going to vanish minus sign by interchanging the limits. So a to 0 e raised to minus x square dx plus integration 0 to b e raised to minus x square dx. Now we know this property of definite integration, that is integration a to b fx dx is always equal to a to c fx dx plus integration c to b fx dx. So you just have to use this property here to complete the example. Here there are two integration, and here upper limit is 0, here lower limit is 0. So this 0 is nothing but c. So we can combine this two integration into single integration as integration a to b e raised to minus x square dx. So we can observe that this is nothing but LHS. So hence LHS is equal to RHS, and example is proved. Let us take a new example. If alpha x is equal to root of 2 upon pi integration 0 to x e raised to minus t square upon 2 dt, we have to show that error function of x is equal to alpha x root 2. So it is better to start from RHS. What is the difference between the given equation and RHS? Here we are having alpha x, and here we are having alpha of x root 2. So here I can just write down, that is replace x by x root 2 in this given equation. So alpha of x root 2 is equal to, better to write down root 2 upon root pi integration 0 to x root 2 e raised to minus t square upon 2 into dt as it is. And now we have to substitute, let t square upon 2 is equal to u square, and therefore we get t is equal to root 2 into u. Let us take dt is equal to root 2 into du, and also limits will change. At t is equal to 0, u is equal to 0, and at t is equal to x root 2, we can write down this as x root 2 is equal to root 2u. In short, we get u is equal to x as the new upper limit, and therefore we are going to write down in this equation now, alpha of x root 2 is equal to root 2 upon root pi integration 0 to, now new limits are x upper limit e raised to minus u square, and now we can see that dt is nothing but root 2 into du. So here we can write down root 2 into du. Here we can observe that we have replaced t square upon 2 by u square, so it is e raised to minus u square. We are going to take root 2 outside, so that we get 2 upon root pi integration from 0 to x e raised to minus u square du. And after simplification, you will observe that this is nothing but mathematical definition of error function of x. So that is equal to error function of x, and this expression is proved. Let us take new example. Complementary error function of minus x plus complementary error function of x is equal to 2. We have standard formula that we are going to write down. Error function of x plus complementary error function of x is equal to 1. So let it be equation number 1. Now this formula is valid for all values of x, and therefore here we are going to write down replace x by minus x. So let us replace x by minus x. We get error function of minus x plus complementary error function of minus x is equal to 1. Now we also know that error function is an odd function, and therefore here we are going to write down minus error function of minus x, and then rather minus error function of x plus complementary error function of minus x is equal to 1. Equation number 2. Here I can write down error function is odd function. So this is the concept that we have used in this example. What we are going to do now, just we have to add equation number 1 and equation number 2. If you add equation 1 and 2, first term gets cancelled, and therefore we get complementary error function of x plus complementary error function of minus x is equal to 2, and the expression is proved. Let us proceed for new example. Integration from 0 to infinity e raised to minus x square minus 2bx dx is equal to root pi upon 2 e raised to b square into bracket 1 minus error function of b. Let us start with LHS. So LHS is equal to integration 0 to infinity e raised to minus into bracket x square plus 2bx dx. For sake of convenience, in the index I would like to convert this bracket in the form of a perfect square. First term is x square, second term is 2bx, means to make a perfect square we need b square, and therefore here we are going to do the adjustment in this manner. X square plus 2bx plus b square minus b square, means in short we have added b square and subtracted b square in the index. Make a group of first 3 terms and second term and use laws of indices. So integration 0 to infinity e raised to minus x square plus 2bx plus b square is nothing but x plus b whole square multiplied by e raised to b square dx. Now next is we are going to take e raised to b square outside. So e raised to b square as well we are going to multiply and divide by 2, as well multiply and divide by root pi to get the definition of error function. So here we can write down root pi upon 2 multiplied by 2 upon root pi. So multiply by 2, divide by 2, multiply by root pi, divide by root pi into integration 0 to infinity e raised to minus x plus b whole square dx. Now to get this term in the form of definition of error function or complementary error function, we need a substitution. So let x plus b is equal to u, and therefore we get dx is equal to du. At x is equal to 0 we get u is equal to b. At x equal to infinity u is also equal to infinity, and therefore we will continue with this LHS root pi upon 2 e raised to b square as it is. Let us put a bracket for this, 2 upon root pi into integration. Now new limits are b to infinity e raised to minus u square du, and then we can observe this bracket is nothing but definition of complementary error function of x. So that is equal to root pi upon 2 e raised to b square multiplied by complementary error function of b. Since the lower limit is b, we have to write down complementary error function of b, and then standard formula, that is error function of b plus complementary error function of b is equal to 1. So this formula we have to use to replace this term as, so root pi upon 2 e raised to b square into bracket 1 minus error function of b. So that is nothing but RHS and given expression is proved.